Our next speaker is Minzer. He tell us about joint work with Noam Lifshitz on noise sensitivity of the bias cube.
Thank you, Luca. Thank you, everybody, for coming to this talk. So I'm going to talk about noise sensitivity on the biased Hypercube. But before we talk about that, let's talk about something more basic, which is sharp thresholds. So throughout this talk, the main object that we'll be studying are monotone Boolean functions over the Hypercube. Where by monotone, we mean that if we have two inputs, x and y, and x is at most y on each coordinate, then f of x is at most f of y. And we'd like to study this function on various measures. And for us, we'll focus on the p-bias measures, which simply mean that you have some parameter p, and each bit is a p-biased coin. With probability p, it is 1, and with probability 1 minus p, it is 0. So what is the most basic thing we can ask about a function on the cube? Well, the most basic thing is, what is the average of that function given a specific measure? Okay, so we can draw this graph of the average as a function of p. So let's assume that f is not a trivial function, meaning it's not constant. Then certainly we know 2 points on this graph. We know that if p is equal to 0, the average is 0, and if p is equal to 1, the average is 1. And besides that, we know that f is monotone, so the curve looks something like that. It's some increasing curve from the 0 point to the 1 point. But what is sharp thresholds all about? So sharp thresholds is about distinguishing this type of behavior and this green type of curve, meaning whether the increase from the 0 point to the 1 point is done in a very short interval or somewhere very wide. And the way to distinguish between these two curves is, well, to look at the derivative of this function with respect to p. If the derivative is large, this is a sharp threshold. If it is small, it is a coarse threshold. So an example for coarse threshold is when you take the function to be the dictatorship function. And an example for a sharp threshold is when you take, say, the majority function. So the general task we would like to study is when does a function have a sharp threshold and when does it have a coarse threshold. So there is one interesting class of functions for which we know quite a lot about. So this is the class of graph properties. And there it was shown by Friedut and Kalai that this interval is always of length at most 1 over log n. And this result was later improved by Bourgain and Kalai, who showed that the interval is at most 1 over log squared n. And this is, turns out to be tight. But the point is that this result is only meaningful when your shift comes at a point which is bounded away from 0 and 1. But what happens if this shift occurs in a very small point? Well, in this case, say if this point is at most 1 over log squared n, then both of these results are quite meaningless in the sense that this interval is always of length at most 100 times this point. Yes, so what do we do when p is small? So unfortunately, there is no general method. I'll try to tell you why there is no general method. But we do know some things, and this is like a central theme in the field. So we have two results. We have a result by Friedut and a result by Bourgain. Don't really care too much about what these results say, but morally, what are they saying? They say the following very interesting statement. They say, if your function is a coarse threshold, then it must have a very local structure. So in the first result, this local structure is the function is essentially a constant width DNF formula. And in the more general result by Bourgain, this local structure means that you can restrict constantly many variables of the function and increase the density of the function by a lot. So this is a general theme in this area, that either you have some random looking behavior that you increase when you increase P, otherwise you have some local structure. And so this talk is not about sharp threshold, it's about something related, but a stronger notion that we call noise sensitivity. So let's talk about that. So here's the definition. So I want to define distribution over inputs that are very correlated. And the way to do that is, so I have some parameter epsilon greater than 0. I sample my point x according to mu p, according to B-bias measure. And now I sample a point y, which is very correlated with x, simply by keeping each one of the bits of y with probability close to 1, and otherwise picking it randomly, according to a p-bias coin. Okay. And now the notion of noise sensitivity is a very simple notion. It measures the effect that this slight perturbation on inputs, the effect that it has on the value of a given function. So again, we sample x and y that are very correlated, and we ask what is the probability that f of x is different than f of y. So we say a function is noise sensitive if this f of x and f of y, they look nearly independent. And if you think about it for a little, what does it mean? It means that this is either 1, 0 or 0, 1, so this is this factor 2, and then you have the probability that is 0 times the probability it's 1. So this is how to write it. And the really other end of the spectrum is a function that is stable, meaning a function for which this f of x and f of y are almost always equal. And it turns out that the right parameter to put here is square root of epsilon. There are reasons for that, but I don't have enough time to go into it. Yeah. So this is the question that we sort of want to address in this talk. What can you say about sensitive functions? When is a function noise sensitive, and when is it noise stable? So this is again the definition of noise sensitivity. So again, as before, we have two regimes. We have the regime where P is bounded away from 0 and 1. This is the one that we are going to discuss on this slide. And there we have a fairly good understanding of this question. There we essentially know the answer. So let's begin with a few examples. So obviously, if you look at the dictatorship, this is not stable. This is not sensitive, and it's very stable. But if you look at majority, well, it is not stable. And on the other end, if you take some generic-looking DNF formula with large width, then this will be sensitive. Yeah. So what are the results that I told you about? So this is two results one by Bourgain and by Binyamin Nicolai and Schramm. So Bourgain proved that as long as P is bounded away from 0 and 1, essentially all of the stable functions are functions that are obviously stable, in the sense that they only depend on constantly many variables. Right? So if your function depends on 2 variables, the probability to change one of them is at most twice epsilon. So of course it's stable. So this is a very nice result, and it has a lot of applications all over the place. And the Binyamin Nicolai Schramm results showed again an if and only if type statement that show that the only functions that are not sensitive are majorities and things that are correlated with majorities. And when I say majorities, I really mean weighted threshold functions, but I stick with the word majorities. Yes, so for P that is bounded away from 0 and 1, we have complete understanding. And this is due to this very important hammer called the hypercontractivity or the hypercontractive inequality, that is really used in both these results and essentially in all results in analysis of Boolean functions. And this is precisely the reason we don't have good understanding for the regime where P is small, because then this tool becomes very weak. We have very poor understanding of this situation. But still, people manage to do stuff, but it's a lot harder. Yeah, so this is the regime that we're interested in. So we care about small p's. So again, the first question that we like to ask is, what functions are noise stable? So again, we have our examples of dictatorship that are noise stable. But here, more generally, any constant width VNF formula is also noise stable. And if you think about it for a couple of minutes or a couple of days, you don't really come up with anything other than DNFs as a noise stable function. So you are tempted to conjecture that maybe these are the only noise stable functions. And this is indeed a plausible speculation, but we could not prove it. So instead, in this work, what we managed to prove is that if your function is noise stable, then at the very least, you are correlated with a constant width DNF. But this is not an if and only if. This is only a weaker structure. Good. So the next question that we'll have to ask is, when is a function noise sensitive? So here the situation is more complicated. Here you come up, as I'll shortly explain, you come up with a speculation, like the DNF speculation before. You think about it, you're convinced that it's true, but then you have a surprise. So again, we have our monotone function, and we want to know when is it noise sensitive. And as before, there are the two suspects for being non-sensitive. These are majorities and constant width DNF formulas, and anything that is correlated with them. You can also show is not sensitive. So this is the very natural speculation that essentially these are the only obstacles to being sensitive. Meaning, if you are not correlated with majority-like functions and constant width DNF, then you are not sensitive. So Noam and I were thinking about this problem, and we thought that this is a plausible speculation. We tried to prove it, and we failed. But we didn't manage to prove some things. So I don't want to state like the most general form of the result. I'll just give you a sample result. So this is the following result. So suppose now your function is very specific. It's some graph property. And furthermore, the P that you care about is very structured. Is like 1 over square root of n or some constant over square root of n, doesn't really matter. Then if you specify yourself to this specific type of functions, then the speculation is true. Being noise sensitive is equivalent to having no correlations with DNFs and with majorities. Okay, but there are two weird things in this result. One of them is, why do you require the function to be a graph property? And secondly, why do you require P to be of this form? So as I already told you, there are variants of these results, but there are two essential features. So we really need a group of symmetries for our technique to go through. So this is why graph property is essential, is useful, because this automatically gives you some group of symmetries, but you can do with other groups. But the more annoying thing for me is that this is a very specific value of P, so it is true that we can do some other values of P, but still it looks weird. Like, why would you have this type of structure of P? Why would you want this form of P? Yeah, so we were able to prove this result, and we're really wondering, like, is this form of P necessary to prove the speculation? So as I told you, we didn't manage to prove the speculation, and there is a good reason for that, that it's simply false. And not only is it false, it's even false for graph properties. So even if you take graph property, but your P is not quite of this form, then there are other functions that are noise sensitive. So there are functions that have no correlation with DNFs and majorities, but are still not sensitive. Yeah, so this result still has some nice implications to noise sensitivity. So using it, we are able to prove that the two-sat function is noise sensitive. And we're able to also give an if and only if condition for the k-sat function to be noise sensitive, which we couldn't prove. But roughly speaking, this condition says that either k-sat is noise sensitive or it has the sharpest possible threshold, like a majority function. And using this criteria, we could also give new proofs for some existing results. Yeah. So I'd like to summarize, pose two open problems. So if there is one thing that I'd like you to take from this talk is the techniques. So I didn't discuss the techniques, but the really essential thing is that we use new hypercontractive type inequalities for the p-bias cube that were recently proved together with Kivash, Long, and Lifshitz. And we also have some variants of classical techniques such as the invariance principle and more for the p-bias cube. So we use all of these things, and this is how we prove our results. So now I want to state two open problems. So the first one is, as I already mentioned, what can you say about monotone stable functions? So I don't know any specific citation, but I believe this is a folklore speculation or hypothesis that this function essentially have to be constant with DNF formulas. So as I said, we could not prove this theorem. Instead, we could only prove correlation. And secondly, about sensitivity, so it would be very nice to find a more general criterion for a function to be noise sensitive, even for graph properties, like for other forms of P. Here we don't even have a conjecture. And also it would be nice to decide whether k-sat has sharpest possible threshold or it is noise sensitive. So we believe it is noise sensitive, but we don't know how to prove it yet. Yeah, that's all. Thank you.
Any questions for Dor?
Yeah.
I might have just missed it, but can you say again what P and epsilon have to do with each other?
So you should think of P as a function of n, like 1 over root n, and epsilon is some small constant.
Just what is a graph property?
Okay. Graph property is when you think of your input as an adjacency matrix of a graph. So 1 specifies that there is an edge and 0 otherwise. Okay, so.
So I think about my input as an adjacency matrix.
Of a graph. Yeah, and a graph property is like, is this graph connected? Does it have a triangle?
It needs to be invariant under isomorphism. That's it.
Yeah.
All right, thanks again.
Thank you.